Hello guys, so today we're going to discuss integral equations, which basically is a very important equation in mathematics, which has direct application to engineering problems, physical systems. We have quantum mechanical systems and physics, even classical physics and electromagnetism. Now, in general, the integral equation has this form. Now we have g of x is equal to a certain function which we call as f of x plus the integral of k xt gt. Let me just write this one properly. We have xt gt dt, and this is evaluated from alpha to beta. Now here we can see that inside the integral, this is what we call as the kernel. And alpha and beta, we have alpha and beta, are actually the limits. Now these are the limits of integration. Now in mathematics, we tend to encounter many integral equations. Now there are actually many forms of integral equations. We have the elliptic integrals and so on. But basically here, we will be discussing only two types of integral equations. Number one is what we call as the Fredholm. We have the Fredholm integral equation. We have integral equation. And secondly, we will be discussing the the Volterra. Now we have the Volterra integral equation. But before we proceed with these integral equations, let me just define very briefly. We're insert this notation here that in general, we can write the linear. Now this is for linear integrals. We have linear integral equation okay, as we have L, we have g of x. This could be equal to f of x, where we have L of g of x. This is g of x is equal to a certain integral. We have kxt gt dt, and this is evaluated from the limits a to b. Okay. Now then, for any constants, we have then for any constants C1 and C2, we have this form. Now we have L times C1 G1x plus C2 G2x, and this could actually be written as C1 times L1 G of x, G1 of x, plus C2. Okay, so this is L. This is C2 L of G of x. This means now we can see that we can actually write this one in terms of this one in the right-hand side, which basically means that integral equations satisfy the linear property. Okay. Now we start with the Fredholm integral equation. They have the Fredholm Fredholm integral equation. Okay, so I believe that we are all familiar with the form now of this integral equation. Basically, this is an integral equation, of the form, okay, we have phi of x, g of x is equal to f of x plus a certain parameter which we call as lambda times the integral of, okay, we have here the kernel kxt gt, we have dt, and this is evaluated from a to b. Now we have to take note here that, okay, we have x and t, okay, we have x and t are between, no? Okay, this is between the limit, or they are between the limits a and b. Okay. Now, here, as what I've said earlier, we have lambda. Let me just, okay. So here we have lambda is a parameter. No? So it's actually a parameter that is mostly given in the problems, in physics problems or even engineering problems. So we consider these following conditions for the Fredholm integral equation. So we have this following conditions. Okay, we have conditions. So if phi of x is equal to 0, we can refer it to this equation above. Okay, so if phi is equal to 0, so obviously everything on this left-hand side would be equal to 0. So we have f of x plus lambda times the integral of k xt gt dt. Okay, so this is what's left, no? Is of course equal to 0, no? And this is evaluated from a to b. And we have to take note here that the limit of the integration, no, for the Fredholm integral equation and for the Volterra integral equation are very important. No? So we really have to remember these limits because that's what distinguishes the Fredholm integral equation from the Volterra integral equation. So we have this one, this is equal to 0, and we call this one actually as the Fredholm integral equation of the first kind. Okay, so this is the Fredholm integral equation of the first kind. Now we have here the second equation, or the second condition for this integral equation. What if our phi of x is equal to 1? No? So we refer to this one. So basically, if this is equal to 1, so what's left on the left-hand side is the g of x. Okay, so we have g of x. Okay, we have g of x is equal to f of x plus lambda times the integral evaluated from a to b of r k xt, this is the kernel, times gt dt. And this is what we call as the Fredholm integral equation of the second kind. Okay, so this is for the Fredholm integral equation of the second kind. Now, that's basically, or these are basically the conditions or the two equations for the Fredholm integral equation. So we move to the Volterra integral equation, and you will notice that really these two integral equations are almost the same. What's different between them is actually just the limit. That is why I said earlier that you really have to remember the limits of integration, because basically that's what separates these two integral equations. So we have the Volterra integral equation. This is integral equation. Okay, now this is basically an integral equation. An integral equation of the form, okay, we have phi almost the same. No? So we have phi of x, g of x. This is equal to, okay, we have f of x plus lambda. We actually just have to copy, no, the, okay, the, what is this, the integral. We have k xt. This is almost the same with the Fredholm gt dt. Let me just write this one properly. So you have, this is gt dt. And from the Fredholm integral equation, we can notice that the limit of integration is from a to b. Okay, this is from a to b. However, in the Volterra integral equation, the limit is actually from a to x. This is the only difference. No? So that is why we can say that if we're going to view this one from the point of view of the Fredholm integral equation, we can see that, or we can view this one. No? This can be viewed, okay, this can be viewed as a special case, of Fredholm equation, Fredholm integral equation. Or let me just write it as IE, integral equation. So this is like a special case of the Fredholm integral equation. So we also have these following conditions, no, or following equations for the Volterra integral equation. We have, what if phi is equal to 0? So we have if phi of x is equal to 0. So basically, we can have f of x. Okay, this is equal to 0, so everything else on the left-hand side is equal to 0. So we have f of x plus lambda times the integral of k xt gt dt evaluated from a to x. Of course, this is equal to 0. And this is what we call as the Volterra integral equation of the first kind. Okay, so this is the first kind. And for the second equation, or the second form of the Volterra integral equation, we set phi of x to be equal to 1. No? So what happens to our equation is that the phi on the left-hand side will be cancelled out. So what's left is the g of x. So we have g of x is now equal to, we have f of x plus lambda times, okay, this is k xt gt dt evaluated now, of course, from this is from a to x, no? Because this is a Volterra integral equation. Now we also consider this case for the kernel. So in general, we have in general the kernel, which as we know is the k xt, is said to be degenerate. Is said to be degenerate or separable. Okay, we have or separable if it can be expressed. It can be expressed. Okay, we have as the sum of finite number of finite, okay, finite number of terms. Let me just erase this one. Okay, so you have terms, each of which is the product of a function. Product of a function of a CS only, okay, and a function of Let me erase this one. S only, and a function of t only. So mathematically, we can write this statement as, okay, we have the kernel k as a function of x and t is equal to, okay, we have, this is the sum, okay, of alpha I x, and this is beta I t. Anyway, this is, okay, x. Okay, and this is evaluated, or this is summation from I is equal to 1 to n. Okay, thus applying this one to our Fredholm equation, okay, we have thus the Fredholm equation. Okay, let me write this one properly. We have the Fredholm equation becomes, okay, so we have phi of x, g of x is equal to, what's our Fredholm equation? Above, this one, no? Okay, so we have phi of x, g of x is equal to f of x plus lambda. Okay, this is evaluated, no, from a to b. And remember that we write the kernel inside the integral sign. So, but the kernel is equal to this summation. So we just have to actually integrate this one or put this one inside the integral. So we have, this is the summation of alpha I as a function of x, and we have beta I as a function of t. And this is from 1 to n gt dt. Basically, no, we really can observe that this is equivalent to our original Fredholm integral equation written above, because this is, as we know, this is the kernel. Okay, so we have k times gt dt. Okay, now simplifying this one, so we have, this implies that phi of x, g of x is equal to f of x plus lambda. So we can actually get this summation out of the integral for these constants, because basically, as we can see, this is dependent on t and not on x. So we can actually write this outside of the integral. So this is lambda times the summation of alpha I x. This is from 1 to n of the integral. Okay, we have what's left in the integral is obviously the beta, the g, and of course the dt. So we have beta I t, we have gt dt, and this is from a to b. Okay, now if phi of x is equal to 1, what happens is that, of course, this would be equal to 1. So we have, we actually just have to cross this out. So we have g of x is equal to f of x plus, okay, we have lambda, okay, times the summation of, what is this, the alpha I as a function of x. This is from 1 to n, and this is multiplied to a certain parameter, to a certain function, which we call as gamma I. So obviously, now if we're going to trace this one, this is f of x, this is f of x, this is the summation, this is the summation. Okay, we have alpha, and this is alpha. So basically, we can see that indeed, okay, we have gamma I is actually equal to this integral term of this equation. So we have, this is the integral of bi times t. Okay, we have gt dt, evaluated from a to b. No? So anyway, we can always write this in terms of this equation. It's also okay. But for simplicity, it's also okay to just write it in terms of this one. No? Okay, but we really just have to remember that gamma I is actually the integral part of the Fredholm equation. Now we can actually solve for gamma I here. No? So we have solving for gamma I. Okay, so we actually can expand this one. So we have f of x right now. We have f of x plus gamma, or yes, gamma times the summation of this one. Now we actually just is just copying this one. Okay, this is from 1 to n times gamma I. Oops, okay. So this is equal to the sum, okay, okay, let me just write this one step by step. So this is actually just the f of x plus gamma times the sum of, okay, this is from 1 to n of lambda of alpha I x times the integral of a to b of bi t gt times dt evaluated from a to b. Obviously, no, we just equalize this one, just to show that indeed they are equal. But we can actually expand this one. So we we can rewrite this one. Obviously, f of x will be cancelled out. So lambda is also cancelled. So we have, this is the sum of alpha I x gamma I. This is from 1 to n. And this is equal to, okay, we have the sum. What's left on the right-hand side is this one. We have alpha x, alpha I as a function of x. This is from 1 to n. Okay, and we have the integral of this one. Now we have bi t. Okay, again, this is evaluated from a to b. However, we can expand this gt. Okay, so this could actually be written as f of t plus lambda times the sum, okay, of say alpha j times t. J is equal to 1 to n, okay, times the integral, okay, of say bj t prime g t prime dt prime, and this is of course evaluated from a to b. Okay, so we have this one. Now if you are curious how we come up with this equation, particularly this one, let me just color it with another color. So basically this one, if you are curious, we actually just repeatedly do the Fredholm equation. As we know, the Fredholm equation has this general form. We have g of x is equal to f of x plus lambda times the integral of, we have the kernel, but we know that the kernel is just a summation times gt dt, and this is evaluated from a to b. And we did the same for gt. So instead of x, why not we use gt? So we have this one, okay, gt f of t plus and so on, where we can come up with this equation. Okay, so of course now there is still dt. Let me change my pen. Okay, we have here dt. Okay. Okay, so we simplify this one. Obviously now this is very straightforward. So this is now equal to the summation. Let me write the summation. Okay, so this is the summation, okay, of lambda I times x. Okay, again, this is from 1 to n, okay, of the integral times the integral from evaluated from A to B. We have beta I t, okay, times we have f of t plus lambda times, okay, we have this one, no? So we have alpha j t. Again, this j is equal to 1 to n. And then this one inside the integral, or this integral form,